You just can't get the thing to work. Just go back and restart. The instructions are pretty detailed. Do this, do this, do this, click on this, upper right-hand corner, lower left-hand corner, and so on. It guides you pretty well through the thing, so that you keep fine and you can help each other. If you're getting stuck, you can look at the people around you. So let's just review what we know. We know that if you have a coil and you try to put current through it, it will resist. And if you have a coil with current in it and you try to shut it off, it will resist. So there's a resistance to changing current. Just like a resistance in a resistor is a resistance to current. The resistance in an inductor, its inductance, is a resistance to a change in current. And so that's the way we think of inductance, as a resistance to change in current. And so if I rewrite this, the voltage induced by an inductor will be its inductance times di dt. And if we set that equal to Faraday's law, then we have, and I'm leaving out the minus sign, n d phi dt, and the phi is BA cosine theta. And in the case of the coil, nothing's spinning and the area is constant. So the cosine is going to be 1. I can take that out. Or I'll just write it out. You cross that out. And so this will be NA, because A is also a constant, dB dt. So NA dB dt is equal to L di dt. And so we have dt on both sides, and if we integrate this, we have NAB equals Li, but this is a coil. So B for a coil is mu naught N over L times I. I'm just write B for a coil. If you look it up, it's mu naught N over L times I. So I'm substituting that in. And that's equal to L times I. And so the I's cancel. And so L for a coil, this is what L is. This is what determines the inductance of any coil. And so what you see is you have mu naught N squared A over L, the length of the coil. So tomorrow in lab, you're going to take a coil and you're going to calculate its inductance using this equation. It's on the equation sheet. So these coils, it turns out, the ones that aren't marked, there's a set of these that are reddish and brash color. Just write this down now because I won't be there. Just use N equals 3,000. They vary a little bit, but that's close enough. So for any of those of this shape and size, the kind of copper colored and the more reddish colored, just use N for 3,000. And so you measure the area, you measure the length, you put mu naught in, and you calculate L. So that's one determination you'll do. And each of you, if you're working in a group of 3, you'll each pick a different coil. And there are these all those coils you worked with last week are in there. So if you got a group of 3, pick a variety. Pick one that's smaller and one that has a lot of windings and one of the bigger ones. Each person takes a different one. But you'll only report your coil. You won't report your partner's coils. But together you'll collect data on 2, 3, or 4 coils, depending on how many people are in your group. And so this is one way you calculate it. And the other way we'll get it is by measuring. We're going to put the coil in an LR circuit. You're going to build an LR circuit. And let's just review what happens in this circuit. So when we close the switch, it's an inductor. So when you have an inductor in a circuit, what does that mean? That means you can't change the current instantaneously. And so that means that the current in the circuit has to start at 0. And there's only one current, right? This is a simple series circuit. So whether I say what's the current through the resistor or the current through the inductor, it's the same current. And it has to start at 0. And what's going to happen? The current's going to slowly rise until it reaches a maximum value where it's constant. And if the current's constant, then there's no change in current, there's no change in flux, there's no induced EMF. And so the current's going to do this. And so that automatically means, this is because it's an inductor, that's the reason, right? It has to go up slowly. If the inductor is slowing it down. And so how about the voltage on the resistor? The voltage on the resistor has to follow the current. If there's no current, there'll be no voltage. And so the voltage across the resistor is going to rise to whatever the maximum value of the battery is, 6 volts. It's going to rise in the same way. And the current through the inductor is going to be the same. How about the voltage across the inductor?
Start the max. Okay.
It's going to decay. So there's 2 ways of thinking about that. One is Kirchhoff's law, right? Kirchhoff's loop rule says that the sum of these 2 voltages has to be 6 volts. So if this starts at 0, this has to start at 6 volts. And when this gets to 6 volts, this has to be 0. And when this is 3, this has to be 3. So it decays to 0. And at any instant in time, these 2 voltages will add to 6. The other way is, as soon as I try to put current in here, the inductor reacts. It sees a change in current, it reacts. And how much it reacts right up to 6 volts, right? Because it can't go more than 6 volts. It's not going to push the current backwards into the battery. It just stops the current. But once the current stops, there's no change, so it doesn't really stop it. It just instantaneously stops it. And as the change in current, you see the change in current is maximum here and 0 here. So the voltage goes to 0. So mathematically and physically, we can see this behavior. So what we're going to do tomorrow is we're going to build this circuit, and you're going to put a voltmeter here and watch that happen. And then you're going to move the voltmeter, because you'll only have one, over here, and you'll see that happen. And these equations are familiar to us. This is the current, and the current, of course, the maximum current, how do we get that? Well, if this is 12 ohms, and this is 20 millihenries. A henry's a big amount of inductance, so I'll make that 20 millihenries. This is 12 ohms. So in the end, the inductor isn't doing anything when the current's not changing, and so the maximum current's going to be 6 divided by 12, right? It's going to be V max divided by R, and so it's going to be a half an amp, 0.5 amps. And so this is going to go, the general equation is I equals I max. Since it's charging, it's 1 minus e to the minus t over the time constant. That's the charging format for the exponential function. And the same way here, so this would be, if we put the numbers in, this would be 0.5 amps, and then we have to find t. So what is t? We talked about this the other day. That's the time constant. And when the time is equal to the time constant, you have e to the minus 1, which is 0.36, which gives you about 0.63. In other words, it goes up about 0.63 of the final value in one time constant. And the time constant is determined by the inductance and the resistance in this way. And you should understand physically why that is. The more inductance the coil has, the more it's going to slow the thing down. And the more resistance you have, the lower the current that you have to get to is. So it actually speeds it up. So by increasing the resistance, I'm only going to go to a half an amp. Rather, if I decrease the resistance, I might have to go to 1 amp or 2 amps. It will take longer. So increasing the resistance lowers the current and lowers the time constant. So in this case, we could calculate what the time constant is. 20 millihenry divided by 6 ohms, and that will give you units of seconds. And so 20 divided by 6 is what, 3.3? I mean 12 ohms? No. Oh, 12 ohms, sorry. So that's 1.66. Somebody do it.
Yes.
1.66 is the milli there, right? So that's going to be milliseconds. So that's the time constant. So when I plot this, I go to about, 0.63, about 2/3, and that's going to be 1.66, and then another time constant, that's 3.33, and then the third time constant, you're about 95% there. 5, right?
Did you get the 0.5 from the V max there? Or
by taking the voltage and dividing by the resistance. So you have to have numbers to get that. Okay, so what you're going to do tomorrow is you're going to graph this and you're going to measure the time constant. And so you will have a resistor which you measure with the meter, and you'll have a time constant which you measure on the oscilloscope, and you calculate L. It's simply going to be the time constant times the resistance. And that L, if you're lucky, will agree with that L. So notice, it's two different determinations. Here, we're getting the L by watching the coil resist a change in current and graphing it. And here we're getting the L just derived from the physical characteristics of the coil. So they're two entirely different measurements. If they don't agree with each other exactly, don't get too worried. And in some cases, we've seen, I mean, if they really disagree quite radically, it doesn't necessarily mean you make a mistake. But in recent years, we've been getting pretty good agreement. And by good agreement, I mean even 40, 50, 60% difference is okay. If it's 10 times bigger, then something may be wrong. But if it's twice as big or 50% bigger, you may be okay. It may be that you didn't do anything wrong. And the important point of tomorrow's lab is more to use this more current, modern equipment and to do circuits where things are changing very fast and you see how to get information. So it's more of a learning exercise than actually. I'm not going to be too concerned if your two values don't match within 15%. If they're within 20% of each other, consider yourself successful on that count. Okay, now just in terms of practicing circuits, and then I'll talk about the lab, let's continue to do this problem. So now we have a resistor of 12 ohms, and this, and when after about 5 to 10 time constants, nothing's going to change, right? This will just sit at 6 volts, this will sit at a half an amp, and this will sit at 0. The current's just going through the inductor, there's no change, there's no induced EMF, and so there we are. But now I take the switch, which is here, and I close it. And so we have a half an amp in this circuit. When I close the switch, there's no battery driving that current, but the current starts to go away. But when the current starts to go away, that's a change in flux, and there'll be an induced EMF that wants to keep the current going. But it can't keep it going, otherwise there's no change in flux inducing an EMF to keep it going. And so what will happen is everything will decay. The current in the circuit will decay, the voltage across the inductor will decay, the voltage across the resistor will decay. And so let's plot that. Now I threw a little twist in here, and that's that I added another resistor, so the time constant's going to change. And just for reasons you'll see in a minute, I'm going to put a big resistor here. I'm going to put a resistor of 2,000 ohms. So what do we have? We have 5.5 amps in the circuit. And so now we want to plot the voltage across the resistor, the voltage across the inductor, and the current through the inductor or through either resistor. Okay, so what do we know about an inductor circuit? This is the thing you gotta remember. How do you start this? Anyone wanna say?
The voltage on the inductor.
What's that?
The voltage on the inductor?
No. The voltage on the inductor was 0. So will it start at 0?
No.
No. Will it start at 6 volts?
No.
It won't. The voltage on the resistor, when I closed the circuit, the voltage on the resistor was 6 volts. The thing that you start with is the current. Why? Because the current can't change. Why? Because if the current changes radically, you get an induced voltage. So the thing that you know for sure, because it's an inductor, is the current is going to start at a 0.5 amp. That's what you know. You're not really sure about these voltages. Well, if the current starts at a 0.5 amp, then the voltage across here is 6 volts. But notice we now have 2 resistors. So this is going to start at 6 volts. Not because it was at 6 volts, but because the current was at a 0.5 amp and has to stay at a 0.5 amp. I mean, it's going to start at a 0.5 amp. So what we know is that this starts at 0.5 amps. And because of that, not because the voltage was 6 volts, but because of that, this starts at 6 volts. Why? Because the voltage across any resistor is a function of the current in the resistor. No matter what, if the resistor has no current, its voltage is 0. So this is where you start, with the current, always with an inductor. Why? Because the property of an inductor is the current can't change instantaneously. Oh, but now we have this other resistor, V2. VR2. So what's the voltage across R2?
Oh, no.
It's 2,000 divided by 25.
So V equals IR. Again, I'm repeating myself, it may not be obvious, but this is what you're going to remember. The voltage across the resistor is a function of the current through it.
1,000.
And there's a 0.5 amp through it. Why? Because it has to start at 0.5. Isn't that going to stop it can't, how is it going to stop the current? If the current changes, then you induce a voltage. So what's the voltage across resistor 2? 1,000 volts. Wait a minute. Where did that come from? It comes from the inductor. Why? Because when this thinks it's going to stop the current, and because it's stopping it fast, that's a big change in flux, and it just keeps going up and up and up and up. The change in flux just keeps rising until this gets to 10,000 volts and does what it wants to do, prevent the current from changing. So what's the voltage across the inductor then? Prof's law.
1,006. Well, negative 1,006, other direction.
Negative 1,006. So we'll just plot the magnitude. The voltage, how did the voltage across the inductor get to 1,000? Because the resistor tried to stop the current. That was a big change in flux, and so it jumped to 1,006 volts.
And so does that mean that it would run out of voltage rapidly?
It runs out of energy very rapidly. Good. Good insight. How do we see that? Let's look at the time constant now. The time constant is now 20 millihenries divided by 1006 ohms. So, no, 1012.
2012.
What is it?
2012.
Oh, 2012, right. Oh, what, did I mess up? I messed up.
No, because that's.
Oh, because it was a half an amp. So call it 2000. So we went from a time constant of 1.66 milliseconds to 10, roughly 10 microseconds. So we reduced the time constant by whatever, not quite 1,000 times, but quite a bit reduced. So this thing is going to decay very fast. Why? Because the energy stored in the inductor, and that you do have that equation I mentioned the other day. The energy stored in an inductor is a function of how much current is in the inductor and the inductance of the inductor. So that energy stored is going to be spent very rapidly. Because why? Because it's pushing a half an amp through a 2000 ohm resistor. That's going to spend the energy very fast. And so the time constant becomes very short. And everything now will decay from 1012 volts, 5 amps. Everything's going to decay according to the same equation. VL equals.
Wouldn't it be 1006 volts? For
Is it
the
1006?
No,
for the
Oh yeah, 1006, right.
because that's just resistor 2, isn't it?
Wait,
Yeah, it's
Wait,
supposed to be
what?
1006 on the inductor. You put
Yeah,
It's
1000.
1006 on the inductor, right? This is just 1,000. Why? Because the voltage across R2 is going to be the current, the half an amp.
It's not quite that. It's just you put 1012 on the inductor. That's just all he is pointing out.
Yeah, it's 6 on the inductor.
It should be 1006.
It should be 1006. Okay. I'm not listening. Are we, everything look okay now? Okay. Anyway, all these decaying equations are going to be something times something max, e to the minus t over the 10 microseconds. And so if you're going to plot this, you're going to plot 10, 20, 30, microseconds. And after 10 microseconds, you've decayed about 2/3, another 2/3, another 2/3. And the decay is going to look something like that. And all of them will do the same thing from whatever starting value they have. Okay, so you're ready to start doing assignment 12 and doing these circuits. I won't be here Friday to help you, so. Sorry.
Where did you get 1006?
So the 1006,
adding the voltages
you
of the
have
two
to add
resistors.
this voltage and this voltage.
Oh, okay.
Net is
The
6
sum
minus
of the
1000.
voltages, that's what I said Kirchhoff's law, the sum of the voltages
Yeah.
around the loop have to be 0.
Okay.
Lab 13 says that it's due at 1:59 a.m. again on Monday instead of 11.
Okay, so I need to fix that. If you don't see it fixed in the next day or so, send me an email. Okay. Okay, so anyway, practice the circuits, help each other out.
Would the other two voltages go down at the same rate?
They're gonna go down at the same time constant, the same equation. If you have VR2, it'll start at 1,000 in decay. If you have VR1, it'll start at 6 in decay. If you have IL, it'll start at 0.5 amp and decay. All at the same rate. Okay, so we only have 2 more days next week. And we still have another circuit to talk about. What we want to do now is bring the capacitor in to the circuit. So we'll do that on Monday. So from now until Monday, try and get as much of this LR circuits done as you can. And if you're getting stuck, like tomorrow or Friday, if you're working on it, help each other out. You'll be able to help each other out. And you can email me if you want.
And that thing works now.
What works?
The question and answer?
The forum.
Oh, yeah, well, that's because you fixed it.
Sort of. Googled it.
Yeah, Sarah figured out how to fix it. I had the wrong forum. Okay, let's talk about the lab. So you see what you're gonna do. The oscilloscope is gonna graph this, and you're gonna use your cursor. You put your cursor here, and you see the time, and then you put your cursor 2/3 of the way down, and you see what the time is, and that'll be your time constant. You're just measuring it off the screen. It's all gonna be plotted on the computer screen. And with that time that you get from the computer screen and the measured resistance, you'll calculate L and compare it to that other determination.
Are you also able to get the time off, you know how like there was a table function where it produced like a table with all
This is a different, we're not gonna use the same
Okay.
setup. And just, it's easy enough to do it graphically. So let me show you. So this is an old style oscilloscope. And this is the function generator. So this will put out a voltage. And this is your voltmeter. And this is your battery. This is a more current digital version of this. So we could use this and this to do the experiment. But we're gonna use this. So this is both of these. Okay? And where it says output, that's the function generator. That's the output. That's the battery. So from the output, I create the circuit. That's my battery.
Is the oscilloscope gonna be like on the computer then?
Just stay with the battery. We'll build the circuit, okay? So you will set what the output is, and you can't control this. You have to control this from the computer. So you will set this up. It tells you how to set it up, and you're going to set it up so that it varies plus or minus 1 volt. And it does it in a square wave. So what it's going to do is, it's going to give you 1 volt, and then 1,000th of a second will be on 1,000 hertz. So frequency, this relationship is important, it's 1 over the period. So the frequency is how many cycles per second. The frequency is cycles per second, and we use hertz. So 1,000 hertz means you're going to get 1,000 cycles, and this is 1 cycle. then it goes to the next cycle, and it's a square wave. It's 1 volt for half of the period. Then it goes to -1 volt for half of the period. And if we're at 1,000 cycles per second, 1,000 hertz, then the period is the inverse of that. It's 1 second for every 1,000 cycles. And 1 second for every 1,000 cycles is 1/1000th of a second per cycle. So this is a half of a thousandth of a second and another half of it. That's 1,000th of a second, and it's going to repeat that every 1,000th of a second, giving you what? 1,000 cycles per second. So why are we varying the voltage so often? Because this half of a 1,000th of a second is within the range of the decay of most of these things. So when the voltage goes high, the voltage across the inductor will go high and decay to 0. This is 0. So you'll see this. And then when the voltage goes low, it will switch to a negative voltage and decay to 0. So if you look at the voltage from the function generator, you see this. If you look at the voltage across the inductor, you see the voltage decaying every time the voltage switches. So you're going to see a repeating pattern that looks like that. Why? Because here it starts at 1 volt and it decays. Here it starts at -1 volt and it decays. Now, if you're looking at the voltage across the resistor, when this starts, it starts at 0 and it rises. Then it goes to -1, it starts at 0 and it rises. Anyway, it's a shape like that. That doesn't seem right. But anyway, you'll see these shapes tomorrow, and you'll see it repeating. So what you're doing is you're charging and discharging the capacitor every half of a thousandth of a second. So what do you need to look at? You just need to look at one of these. So if you go to this one, I know it started at -1. And it goes like this. Anyway, this one's easier. It starts high and it goes towards 0. Then it goes low and it goes towards 0. So what you do is you look at this. And if you see this, it's not quite flat. So what you would do is you would adjust the frequency lower, so that you would make this longer. So what you want to see is something that starts and goes like that. And you don't want to see something like that because you want to stretch this out. But you don't want to stretch it out so much that you don't see the end. And how do you adjust that? You adjust that by adjusting the frequency, which will change this. And I did one this morning with this coil, and the 1,000 hertz was just right, actually. But as you change the coils, you may have to, in this case, increase the time to see the rest of the decay. Or in this case, decrease the time, because you just want to see this part of it. And you want to expand that. So once you have the shape that you want, you just look here and you look here, and this morning for me, that was 1.5 volts. From here to there, it became 1.5 volts. So I say, okay, so 2/3 would be 1 volt. So I look at what the time is at the top, and then I bring my cursor to where it's 0.5 volts. So it's decayed 1 volt out of 1.5 volts. That's about 2/3, that's about the time constant. And then I measure the time there, and that time difference is my time constant. And what I got numbers like 2.6 times 10 to the minus 4th seconds, and 3.8 times 10 to the minus 4th seconds. And so the difference between those would be 1.2 times 10 to the minus 4th seconds. That would be my time constant, the difference between those two times. So here's the output. And notice that there's a bunch of chords in there that are banana chords. And so whenever you have a banana plug, just use the banana chords. But if you need an alligator clip, just take one of the alligator clips and you can put it on the banana end, and then you can clip it, say, to the resistor. And so I did that here. And then, so the current comes out, goes through the inductor, goes through the resistor, and goes back there. And this square wave is going to be put through this circuit. So now I want to read the voltage here. So here's my voltmeter. This is the thing that's going to read on the screen the voltage, right? What this is plotting is the voltage as a function of time. So if I want to read the voltage across the inductor, I just do this. Right? I'm just putting the voltmeter across the inductor, and when I start the square wave, I'll see this. And you just start it and stop it because it'll plot it. You don't need to let it run. Just start it and stop it, and then you'll have that graph frozen, and then you can go and read the readings. So then, when you want to read the voltage across the inductor, across the resistor, you just go here. So I could put clips on here and clip to the resistor, but I see I already have these banana things here, so I could just plug in here, and now I'm reading the voltage across the resistor. So this is your meter, which is the oscilloscope, and this is your function generator, which is the battery. See how easy it is? You'll have fun. This is a very nice lab. Enjoy it. You're on your own. It'll be much more fun than anyway. You don't use me anyway. You figure these things out on your own. I just sit in my office, so you don't need me. Anyway, this is a very nice lab. I hope it works well for you. See you Monday.